Okay, we're now going to talk about the issue of special relativity. And special relativity is a very important subject in physics. It describes how things behave, how matter behaves, and how light behaves when we approach things close to the speed of light, speeds close to the speed of light. Um, or at least speeds that are somewhat appreciable compared to the speed of light. Um, and the effects that we are going to discuss here do not really manifest themselves in our daily life, simply because the things that we observe, things like a car moving down the street or an airplane flying through the sky, or honestly, even spaceships flying through, to the moon and back, their speeds are just simply not fast enough for the phenomenon that we're going to discuss here to really manifest themselves. And this is why, partially, it took so long for things like the um, uh, theory to manifest. Why it took so long for us to understand. And so that's where we're going to start. The theory of relativity really has to do um, again, with things like the speed of light. One consequence of the theory of relativity is that as far as we are aware, right, as far as we are aware, no object with mass can travel as fast or faster than the speed of light. The speed of light is the universal speed limit. So for the moment, if we want to get into a spaceship and travel somewhere, especially at modern day speeds, we are going to be restricted by the issue of the speed of light, and we're going to be bound by that law as for the foreseeable future. Now, there are potential ideas, particularly if you've seen things like the movie Interstellar. Uh, there are potential loopholes via things like wormholes, or if you're a Star Trek fan, using the warp drive to warp space time and things like that. But using classic technology, regular rocket propulsion, we're bound by the fact that we cannot travel faster than the speed of light. So, if we want to pursue interplanetary travel, go to other star systems, this is going to take a really, really, really long time. Now, a little bit of a historical sketch. Um, in the at the turn of the 1800s to the 1900s, um, physicists were mostly comfortable with where we were at in terms of our base of knowledge. And we had a pretty good grasp of mechanics thanks to Isaac Newton. We had a very good grasp on things like thermodynamics. We had been able to build things like the steam engine and build refrigerators. So we understood thermodynamics. Thanks to James Clerk Maxwell, we understood electromagnetism. And so physics was in a really good spot. Pardon me. We understood a lot about the universe, or at least we thought we did, but there were still some things that eluded us. In the early 1800s, it was shown that light behaved like a wave. And um, everybody pretty much accepted the result from the Young's double slit experiment. And Maxwell's equations also helped verify from a theoretical point of view that light behaved like a wave. But there was still a question, and that question was, and every other wave that we knew of, particularly waves like sound waves, require a medium to travel through. It's the disturbance of the medium itself that allows the wave to propagate. And water waves behave like this. If you watch a rock thrown into a pond, you'll actually watch the water um, be the medium that the water wave travels through. Air is the medium that sound waves travel through. When you pluck a guitar string, the string vibrates up and down, and that is the medium that the wave on the string travels through, and so on. And so we had a really good understanding of waves. And so we did not know what it was that light, we didn't know what the medium that light propagated through. It was hypothesized um, that there was a substance called the ether. And some people spell it slightly different ways. Um, we'll, uh, we'll spell it like this: the ether. Okay. Um, and so the idea was just like with sound waves or water waves, imagine being on a boat, okay, and someone throws a really large rock into the water, okay. If someone throws a large rock into the water and creates really big water waves, imagine being in a boat and you turn your boat straight into those water waves and turn your motor on full throttle. And when you do that, you're going to hit the crests of the waves faster than they would hit you if you were stationary in the water with respect to the shore. And if you travel away from the water waves, the crests will hit you more slowly. And so this led to the idea of, well, if there's ether permeating the entire universe, and this is the medium through which light travels, then we should be able to detect the motion of the Earth through the ether by variations in the speed of light. And so the idea is if you measure the speed of light in one direction and you measure it in a perpendicular direction, if you're traveling into the ether, like you're traveling into the water waves, you should see the waves coming at you faster than if you're traveling perpendicular to the medium. So if you're traveling perpendicular to the water waves, you'll notice that they're hitting you at the same frequency that they would hit somebody just standing in the water. And so the, the way to try and measure this was done with the Michelson-Morley experiment. And so the Michelson-Morley experiment is set up like this. You have a light source. Now, the idea that this is a coherent light source is important. The coherency means that all of the waves coming out of the source are in phase. And so what that means is if you think of the light coming out as a wave, every beam of light that comes out is going to, why am I doing that? Huh. Okay. Um, well, for the moment, I'll erase that in here in a minute. But imagine all of the light coming out of the source is in phase where all the crests line up, troughs line up, crests line up, troughs line up, crests line up, so on and so forth. That is the idea of coherency. Okay. So, that is what we mean by coherent light. And if you have a coherent light source and you shoot that light source at a reflecting mirror, okay, if it's at 45 degrees, then the light will be sent perpendicularly to its original direction. But this isn't just a regular reflecting mirror. So this is a semi-silvered mirror. And so what that means is it's going to let some of the light reflect and it lets some of the light through. but the other side is also semi-reflective. Okay, so some of the light will come through. Oh no, I apologize. The backside is purely reflective. It is not transmittative. Um, and so what this means is, if these mirrors are situated at the right points, then the light recombines at this point, okay, and it gets reflected down to the detector. And if the waves are out of phase at all by the fact that the Earth is traveling into the ether in one direction and perpendicular in the other, then the two beams of light should not be able to recombine perfectly because their frequencies should be shifted. Um, and so you would expect a very strange interference pattern at the detector. But this is not what was observed. And it didn't matter what direction they pointed their apparatus, they just were not getting a different result. And so it was concluded from the Michelson-Morley experiment that the ether did not exist. So that meant that space is a vacuum. Okay, there was no medium in space for the light to travel through. So remember, light is electromagnetic fields, alternating electric and alternating magnetic fields. And our current understanding is that these fields can propagate through space, through a vacuum, with a definite speed. And so the speed of light was known, at least to some precision, by the time Michelson and Morley did this experiment. And the results of this experiment led Albert Einstein to propose. Now, I really should be very careful here. Einstein did not propose special relativity because of the Michelson-Morley experiment exclusively. There were a host of things that were going on that caused Einstein to work on the special theory of relativity, but the Michelson-Morley experiment was one of the keys. Okay, and so when you have light moving through vacuums and the speed of light seeming to be constant in all directions, regardless of how you're moving, this was a rather startling conclusion. Again, all of our previous experience with sound waves, water waves, and any kind of wave we'd experienced before really had shown that the frequency you observe is dependent on your velocity. This is the entire Doppler shift idea. Um, and kind of seeing a negative result here was fundamentally groundbreaking and paradigm shifting. And so Einstein took this result at face value and said, okay, if this is the case, then we're going to claim that light is in fact constant in all directions. So this is one of Einstein's postulates. Now, his first postulate that he wrote down when working on this was that um, the laws of physics are the same for an inertial reference frame. Okay, so the laws of physics are the same in an inertial reference frame. Now, what's an inertial reference frame? Okay, an inertial reference frame, I'll label this inertial reference frame, is a frame or a coordinate system, if you want to view it that way, a frame where Newton's first law is valid. So remember Newton's first law. An object at rest will stay at rest, and an object in motion will stay in motion unless acted on by a force. And so, what Einstein is saying here is if I'm in an inertial reference frame, if I'm in a frame that has constant velocity, whether that velocity is zero or some positive number in magnitude, then I will not be able to distinguish that I'm moving if unless I can view the outside world, right? So imagine if you were in a train car. If you were in a train car that was, for example, say a maglev train, and it were on a perfectly straight track and it were moving at a perfectly smooth speed, it wasn't speeding up, slowing down, and it wasn't going around turns. Um, and it was completely boarded up. There were no windows and there were no doors, um, or the doors were sealed anyway, whatever the case. You wouldn't be able to perceive that you were in motion. And so Einstein says, even if that object is moving relative to the ground, you would not be able to perceive that you were in motion unless you could look outside and see the ground, right? Unless you could see mountains and trees in the distance and see that you were moving past. If you shut the windows back up, you would not be able to know. So you could do anything that you could do at rest on the ground. You could play basketball. You could play catch. You could drop things and see them fall straight down. And all of the laws of physics would be the same. You would conclude that Newton's laws held, and all of the other laws, the laws of rotational motion and all those kinds of things, held as well, as long as you were in that reference frame. So there's no what this law is saying is there's no way to tell that you are in motion relative to something without making reference to that other reference frame. Uh, in this case, say someone standing on the ground and watching the maglev train pass. The person on the ground would measure the maglev train to have some speed if they had a radar gun. But if you on the train did the same thing, you would measure them to have the same speed moving away from you. And so the train could be thought of as stationary, and the observer standing on the ground is receding from the train just as easily as the train would be moving away from the person on the ground. So this is where the whole idea of this relative motion notion comes from, right? Um, but to correlate with that, the second postulate comes directly from the Michelson-Morley experiment, and that is the speed of light is constant in all inertial frames. So it doesn't matter what frame you're in, you will always measure the speed of light to be c. Now, this is, I just said something and I didn't clarify. We use the letter c to represent the speed of light. And currently, the accepted value that most introductory textbooks quote will be 3 times 10 to the 8th meters per second. It turns out that it's actually 2.9979 and some change times 10 to the 8 meters per second. But in most cases, 3 times 10 to the 8 meters per second is perfectly sufficient. Um, and so, what the second postulate here is saying is that, let's label these Einstein's postulates. What this postulate is saying is that even suppose if you were in a spaceship that was traveling half of the speed of light, if you were in a spaceship that was traveling at half the speed of light and you shot a laser beam in front of you or headlights in front of you or whatever the case was, if you could measure the speed of that beam, you would still measure it to be c. You wouldn't measure it to be half of c. And if you shot a beam behind you while you were traveling at half the speed of light, you wouldn't measure it to be 1.5 c. You would still just measure it to be c. So this posed some interesting consequences. Number one, there's a principle in relativity called simultaneity. And how do you measure two simultaneous events? Well, most people would say, classical physics would say, that two things that happen at the same time have to happen at the same time according to any observer. No matter what's going on, the two observers would have to observe simultaneous events at the same time because time is immutable. Well, we have three quantities when we're talking about the mechanics or the dynamics of special relativity. Those three quantities are time, length, and speed. And as we all know, we'll represent these with these variables. Okay, so remember that speed is just equal to distance over time, right? So Newton says that time is constant. And so therefore, anything that happens between two different reference frames must be a consequence of the fact that the lengths might be different and whatever the speed is relative between the observers. But Einstein says, well, what happens when we incorporate light into that kind of construct? So consider what we have here. Here we have an individual on a train, and we have light coming to them from two different lamps, and these lamps are equidistant away. So in the train's frame of reference, if the train is moving, and might make that a little bit larger, it's moving with a speed v, if this train is in an inertial reference frame, as long as v is constant, Einstein claims, and you would observe this, we've actually done this, both beams of light, if the light bulbs turn on at the same time, they emit the light at some time, say t equals 0. Let's say t initial equals 0. That's when the light starts, and observer A will see the light from both lamps hit her at the exact same time. So t final would equal some time, whatever that time might be. But observer B, standing outside the train, if he has a window eye view of this, he would see the light from this lamp hit observer A before the light from this lamp hit the observer. Okay? So because the train is moving away from this lamp and moving into the light from this lamp, just like with the waves and the boat, these waves here are going to get to observer A faster according to observer B. Observer A says they happen at the same time, and observer B says the light from the right lamp gets there first. So we don't have simultaneity in this case. Okay, this breaks the idea of simultaneity. And the reason is because now when I'm talking about the speed of light, the light coming out of these lamps, I have c is equal to x over t. But before, in the Newtonian construct, we said that the time was constant, so the speed was what mattered, and therefore the length changed between two events. But now Einstein is saying, no, the speed is constant, so it's both then the length and the time that change. So things can happen at two different times according to two different observers. The same thing can happen at two different times according to two different observers. That thing in this case being that light from two lamps hits observer A. Observer A says they happen at the same time. Observer B says no, they do not. And this is a very strange thing indeed. It gets even more bizarre. So if you consider a person on a spaceship doing an experiment where they um, let's so I'll draw this just a little bit bigger. So imagine you have a light source here and you have a detector right next to it. Uh, that'll be good enough. Okay, and you have a mirror up here. If the spaceship is flying in an inertial frame, they just so the light source sends a beam up to the mirror and comes back down to the detector, and they would measure some time interval for that to happen. So if you had a clock that measured the amount of time it took to send the beam out and then to come back to your detector, you have some clock that measures that time interval. We'll call that T0. Okay. Um, what you would see if this is a distance d apart, okay, then you would just say, okay, that minus whatever slight angle this was at, but if these are really, really close to each other and this is effectively straight up and down, then you would say the distance that was traveled here was equal to c times 1/2 the time interval that you measured. And that's because the 1/2 comes from the fact that it would take um, light half of the total time to get up here and then half the total time to come back. So that distance by itself would be equal to c times 1/2 the time. But Einstein says, well, what would an outside observer see? What would somebody outside the spaceship observe? They would observe the light beam traveling in a much larger triangle. Because the spaceship is moving this direction with some velocity v, therefore the mirror is going to be significantly further um, away from the initial starting position. So the beam has to take this triangular path to then get back down to the receiver. And so these two paths, this path and this path, are not the same. And so Newton would reconcile this by saying the speed that we would observe for the light would change because the time had to be the same. So the speed the light would have would be equal to some combination of its own natural speed c plus the speed of the spaceship v. And that would account for the fact that these two paths are different. But Einstein's saying that since the speed has to be the same, the speed of light has to be the same in both cases, it's the distances and the times that don't match. And so what Einstein realized out of this is for an observer outside, they would measure a time. So let's actually let this be delta t, not, and the clock for the outside observer, let's let that be delta t. And so what Einstein realized is that time between two reference frames is related by this equation. And you'll notice the clock here has a longer time interval than the clock according to the spaceship or according to the astronaut. So, and that's a consequence of the fact that it took a longer path. So if the speed of light is constant and it went a longer path, then it must have taken a longer time. So these two clocks are found to be related to one another by this formula. Okay? The time measured by the stationary observer would be equal to the time measured by the astronaut divided by the square root of 1 minus v squared over c squared. And so, as a result, these two clocks are not going to agree. What are the consequences of this? Okay, so this is the famous time dilation. Okay, this is known as time dilation. And sometimes people write this 1 over the square root of 1 minus v squared over c squared as the term gamma or the factor gamma. So one way you could write this would be that the time interval from the stationary observer would equal the time interval on the spaceship times gamma. Okay. But gamma just means 1 over the square root of 1 minus v squared over c squared. And all of this is square rooted. Okay. So it's the fact that c is so fast compared to our everyday standards that we just do not observe this. So if I were to plug in like a standard highway speed of like 70 miles per hour, into this calculation, convert that into meters per second, square it, and divide it by 3 times 10 to the 8 meters per second squared, I would get a really, 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 really small number. And 1 minus a really small number is essentially 1. The square root of 1 is 1. And so gamma is effectively 1. So the clock, according to your car, and the clock, according to someone standing on the side of the road, actually it would be the other way around. T0 is the clock in your car. Delta T would be the clock of somebody hitchhiking. They're going to agree. And to the precision that our Apple phones and smartphones and car clocks, computer clocks, all those kinds of things, the precision that they carry, they're not going to detect this phenomenon. Okay? They're just not. But we can detect this phenomenon in places like particle accelerators. Now, as an example, okay, let's suppose I have an observer on Earth and they're watching a spaceship fly away, and this is future technology, right? Despite how bad my cartoon is, this is future technology, and let's say that the velocity of the spaceship is 0.8 times the speed of light. Okay, so it's 80% the speed of light, right? So um, if if an astronaut in the spaceship measures a time interval, let's say of let's say 1 minute, 60 seconds. Okay, so an astronaut looks down at their watch, they measure 60 seconds. How long would a clock on Earth tick off? Okay, how long would a clock on Earth tick? So we can say that this is going to be equal to delta T naught over the square root of 1 minus v squared over c squared. And this is going to be equal to 60 seconds divided by 1 minus, okay, now 0.8 c divided by c, and both of these are squared. So let's look at this term 0.8c squared divided by c squared. So this is the same thing as 0.64 c squared divided by c squared. So the c squareds cancel out, and I'm left with just 0.64. So this is 60 seconds divided by 1 over, or 60 seconds divided by the square root of 1 minus 0.64. Now 1 minus 0.64 is equal to 0.63, I'm sorry, 0.36. So 0.36, so this is 60 seconds over the square root of 0.36. And the square root of 0.36 is equal to 0.6. So delta t is equal to 60 seconds divided by 0.6. Okay, so it turns out that uh, dividing by 0.6 is really close to multiplying by 1.6. But if we do the calculation explicitly, we would get 60 seconds divided by 0.6 gives me 100. So 100 seconds would tick off a clock on Earth relative to 60 seconds ticking off inside the spaceship. Now, here's a really mind-twisting thing. As long as the spaceship is simply heading away from the Earth at that speed, or toward the Earth at that speed, either one, then the observer in the spaceship would measure the same phenomenon for a clock on the Earth. Because remember, the clock on the Earth could be considered moving, and the spaceship could be considered stationary. And so the astronaut would say that 60 seconds on Earth is worth 100 of his seconds. And the question is, who's correct? Whose clock is actually faster? Whose clock is slower? The answer is, as long as this motion is constant, both clocks are correct. That's a fairly mind-numbing thing. And so, what else did Einstein say? Right? What else did Einstein say in the theory of special relativity? Number one, so this is time dilation. Einstein also said that there's such things as length contraction. And so things get smaller, okay? Things get smaller. The change in the length of an object is equal to whatever that object's original length is, in this case, divided by gamma. So how much smaller an object looks is equal to the square root of 1 minus v squared over c squared times the length, okay? And he also says that objects experience mass dilation. So an object in a frame of reference that is inertial will measure its mass. Let me say that the frame of reference would be considered the stationary frame. Is going to have a mass m naught, and people measuring that, if that object is moving at some velocity relative to another frame, just like the spaceship moving to an observer on Earth, the observer on Earth would measure the mass to be equal to the mass measured in the inertial frame minus divided by the square root of 1 minus v squared over c squared. So both of these phenomenon we've measured. Okay, we've measured these phenomenon many times over. Two of the dynamic properties of relativity are momentum and kinetic energy. And normal momentum says P is equal to mv, right? So an object's mass times its velocity. But when you start to get velocities high enough that this ratio becomes appreciably larger than 0, then this changes, and it is in fact equal to gamma m times whatever the velocity of the particle is. So this is the relativistic momentum. And kinetic energy is equal to um, the rest energy of an object times gamma. Now, a consequence of the special theory of relativity was Einstein's famous equation. So E equals mc squared. Okay, E equals mc squared. What this equation is really saying is that this is the rest mass, or I'm sorry, the rest energy of an object. Okay, and this m is the rest mass. Okay, but when you are moving, so in other words, if I had a proton that was stationary and I measured the energy of that proton in a relativistic sense, the total energy content of that proton would be equal to this number. So m naught would be the mass of a proton measured in the laboratory. Okay. And I can convert that into energy by multiplying it by the speed of light squared. But the relativistic kinetic energy is equal to the rest energy multiplied by gamma. Okay? So, for example, if I had let's do a quick example. I'll block off some of the slide here. If I have a proton and actually, you know what? I'm going to create a new slide. I apologize. So we have that, we have that, we have that. So first things first, right? If I want to use this formula, let's suppose that I have a proton, and a proton's stationary mass is 1.67 times 10 to the negative 31 kilograms. Or I'm sorry, negative 27 kilograms. Okay, 1.67 times 10 to the negative 27. And let's let the speed, and once again, be 0.8 c. And the reason 0.8 c is nice is because the square root comes out to be a nice number. It's really easy to do the mathematics. So what is the relativistic energy in joules? Okay, so let's actually find the rest energy, and then B, we'll find the relativistic energy. So E naught is going to equal mc squared. Okay, so this is just going to be 1.67 times 10 to the negative 27 kilograms times 3.0 times 10 to the 8 meters per second quantity squared. And when we do that, we're going to get something like, if I plug that into my calculator, we get 1.5 1.5 times 10 to the negative 10 joules. Okay, not very much by human standards, right? Not very much by human standards at all. So what happens then? Okay, what happens then to calculate the relativistic? So the relativistic energy, when it's moving with this velocity, is going to be equal to this 1.5 times 10 to the negative 10 joules divided by the square root of 1 minus 0.8 c divided by c, quantity squared. And so this is once again 0.8 squared is 0.64. The c squareds cancel out. So this is 1.5 times 10 to the negative 10 divided by 0.6 once again. And if I divide that by 0.6, 1.5 times 10 to the negative 10 divided by 0.6, I'm going to get 2.5 times 10 to the negative 10 joules. Now, there's one more thing here, and that is the issue of electron volts. So electron volts are a unit of energy, okay? And it turns out that, so an electron volt is the amount of energy it takes to move an electron through 1 volt of potential difference. So if you remember, well, I don't know if you may have known this or not, but it takes an amount of work to move an electron through an electric field, and that work you can consider energy. And so when I have an electric field and I move that electron through it, it's going to be moving through a potential difference as it does so, and the amount of work that it takes me to move that is going to be called the electron volt. So it turns out that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. And that's just because if I compare 1 volt times the charge of an electron, the charge on the electron is 1.6 times 10 to the negative 19 coulombs. So this is where that conversion factor comes from. So because when we're talking about subatomic particles, these joule answers are going to be relatively small. So it's often easier to talk about things in terms of electron volts, okay? Or sometimes even mega electron volts. So, for example, if I wanted to know what A is in electron volts, okay, then I'm going to have 1.5 times 10 to the negative 10 joules. I'm going to multiply that by the conversion factor of 1.6 times 10 to the negative 19 joules in 1 electron volt. So I'm basically going to take my 1.5 times 10 to the negative 10, and I'm going to divide that by 1.6 times 10 to the negative 19. And this is going to give me 9.38 essentially times 10 to the 8 electron volts. And 1 mega electron volt is the same thing as 1 times 10 to the 6th electron volts. So this would also then be equivalent to 9.38 times 10 to the 2 mega electron volts, or 938 mega electron volts. So the rest energy of a proton is equal to the amount of energy equal to 938 million times the amount of energy it takes to move 1 electron through a potential difference of 1 volt, right? So that's a lot. And if I did the same thing converting part B into electron volts, then I'm not going to write out the conversion because we already did the conversion in this first part here, right? But um, so if I look at the second part here, if I take 2.5 times 10 to the negative 10, and I divide that by 1.6 times 10 to the negative 19, then this is going to be 1.56 times 10 to the ninth electron volts, which would be 1,560 mega electron volts. So once you get protons moving, okay, once you get protons moving, their total energy goes up. And so this is a fundamental point. Your total kinetic energy cannot be less than your rest energy, because your rest energy is just when you're sitting there, right? And so as you're moving faster, you're gaining more kinetic energy, so your total energy goes up. And in fact, it will go up exponentially as you approach the speed of light. And so what that means is, if you're looking at the momentum, now this graph would hold for energy as well. You could put energy on this axis as well, not just the momentum, because they both go up by the same factor of gamma. So whatever your speed is, that's is going to determine the shape of this graph. But as I approach the speed of light, my momentum and my energy get higher and higher and higher, and they will approach infinity. Okay. Now I can't reach the speed of light, but I can get arbitrarily close. Okay. And so as a result, when I plug in larger and larger fractions of c into this equation, like for example, if my velocity were 0.999, that times the speed of light, then I would get a very a fraction here very close to 1. 1 minus something very close to 1 is going to give me a very small number. And when I take the square root of that, it's still going to be small. So I'm dividing this numerator by a now very small number, which will increase the total result by a lot. And so as a result, your relativistic energy and momentum are going to increase very rapidly the closer to the speed of light you get, right? One of the places that we observe these kinds of effects most importantly are in particle accelerators. So this is the Brookhaven National Laboratory. We also see these effects very, very prominently at places like the CERN Super Collider, because these kinds of colliders can accelerate protons up to things like 99.999% the speed of light, right? And so when you have speeds that are that high, these relativistic effects become very, very important. Other places that we see these are in the lifetimes of particles that are created in decay experiments. So if you smash particles into other particles, and you can create things like muons. Muons are known to have a specific half-life. They decay rather rapidly, but we're actually able to observe them in our laboratory uh, beyond what their lifetime is supposed to be, because they're moving so rapidly that due to time dilation in our frame, we see them exist longer than they exist in their own frame. And so we can actually do experiments and measurements with them because they exist longer according to our frame of reference than they do in their own frame of reference. So this is not simply academic and trivial. We've done these things. By the way, I should mention this. We have tested this idea of time dilation very thoroughly. Um, this time dilation, you have to take it into account when you have GPS satellites orbiting overhead, because they're moving very rapidly compared to us. And so even though they're still not moving very fast according to the speed of light, it is fast enough that this v squared over c squared term does not stay negligible for very long. And so the little tiny errors that build up each second, even though they're very tiny, over a long period of time, they do add up. And so our computers on our GPS satellites are constantly taking this into account. Um, we also have done this on airplanes with very, very fast jets and atomic clocks. We have synchronized atomic clocks on the ground and then put one on an airplane and let it fly around the world as fast as it could a few different times, a few times before it landed. And the speed of the airplane was known, so we could plug the speed of the airplane into this formula and predict how far off the two clocks were from each other. And in fact, that is exactly what we found. So we have tested this idea and many times over. And as far as we have seen, with the idea of special relativity, Einstein has yet to be shown to be wrong by any experiment. So, for the moment, the special theory of relativity is universal. As far as we know, it holds everywhere in the universe. And one of the more bizarre kind of ideas because time is no longer immutable, time is no longer a constant flow. Two things can be true at once. My clock can run fast according to yours, and your clock can run fast according to mine. And both clocks are correct. Both interpretations are correct. So it's very, very bizarre. But this is what the special theory of relativity says. And we have verified this many times over in places like particle experiments, particle colliders, and so on. So, as far as we know, it's true, as bizarre as it may be. So, I hope that seeing some of these calculations done allows you to do some of the calculations yourself with some confidence. And we will see you in the next video.